next speaker is a colleague of Bob's at Princeton. So I've asked Bob to do the introduction because he knows Andy way better than I do. So if you kindly give an introduction, that'd be great.
Yeah, so it's my pleasure to introduce my colleague and friend and brother in Christ, Professor Andrew Bocarsly, who's a professor of chemistry at Princeton. It has done research in a wide variety of areas, and one of the things he's going to be talking about is a very important issue, which is CO2 and its relationship to the environment and the various issues related to it that he's going to address in his talk.
Bob arrived at Princeton just a couple of years before I did, and he was one of the first faculty members that I met that wasn't in the chemistry department. So I've known him for a long, long time. But maybe more importantly with regard to this meeting is I don't think I'd be standing here today if it wasn't for Bob, because it was about a decade ago that Bob invited me to talk at an ACS annual meeting that he was organizing. And that was part of my introduction to the ACS, and we've been involved since then. So, ASA. Did I say ACS? ASA, I'm sorry. I'm a chemist. So I have to, ASA. Along those lines, by the way, you just heard about MEVs and pretty high development levels compared to where I'm at. So I need you to now lower your expectation thinkings down about 1 EV so I can talk to you about chemistry and stuff that's at a TRL level of 2 if we're lucky. So you were complaining, but I'm not even there yet. So we have been working on the idea of CO2 utilization for quite a few years now. That is taking carbon dioxide, which we probably don't want in the atmosphere, and turning it into something that would be more useful. So doing some chemistry on it and doing that in an energy efficient way. And I will tell you a little bit about what we're doing today, but really what I really want to focus on today is the whole issue of do we have the willpower to do this? Are we going to actually do these sorts of things? Not just my chemistry, but anybody's ideas, Bob's ideas, 1,000 other ideas that we've heard here. So I'd like to start with that idea. And my first thinking is just a very human idea, and that is, seems like the whole idea of mitigating climate change is a matter of self-preservation. So shouldn't it just be obvious to everybody, forget about your religious position? Now, we want to do this. Now, I understand that there's a variety of opinions, and some people think this is an issue and some people don't, but there was some information talking yesterday that suggested, at least in the United States, about 70% of the population thinks that, at some level anyway, climate change is something that needs to be dealt with. Of course, that means 30% don't believe that, but okay. But you know, down south, where I come from, we've had some really hot weather, as has southern Europe this summer. And of course, up here, I pulled that fire map down last Tuesday, 800 plus fires, many of them the red dots are the uncontrolled fires. And by the way, that's only been a problem for you guys, but we actually closed the chemistry department at Princeton for 2 days earlier in the summer because there was so much smoke coming down from those fires that it became a health hazard. It's a North American problem, not a Canadian problem. And then I just pulled this one headline down from the World Weather Attribution. Again, this is a science group, and you can agree with them or not agree with them, but I'll just note this summer's heat wave, talking about this summer, would have been almost impossible without human-caused warming, a new analysis shows. So we are starting to reap the benefits, if you will, or the penalty of climate change, which I believe is due to excess CO2 in the atmosphere. And yet, even though we're understanding this and we're hearing about various health reports, we haven't done anything about it yet. And I think in part we haven't done anything about it, lots of reasons, but a lot of the aspects of the problem, I think, are still hidden to us. That is, there are irreversible changes that haven't occurred yet, but will occur, and it's going to be impossible for us to do anything about it at the point they occur. But they're hidden problems. So for example, we're starting to see a little bit now, but there are going to be changes in atmospheric and ocean currents according to my geoscience colleagues. And of course, once that happens, once you break a current, you're not going to get it back. And that's going to have big impacts on our climate. Something that I'm very familiar with and want to talk a little bit more about is the acid buffering capacity of the ocean. About half of the CO2 that we are generating and nature is generating ends up in the ocean. So if we didn't have an ocean that absorbs CO2, we'd have twice as big a problem, in other words, than we have today. And that buffering action has a capacity associated with it. There is a buffer capacity. And if you break that buffer capacity, you cannot get it back. Okay. So we're not at breaking buffer capacity yet, and we'll all figure it out when we do break it, but at that point you can't do anything about it. So that's hidden. And then, of course, we hear a lot about disruption of ecological communities, that various species are dying out and whatnot, and both animal and plant. And of course, once a species is gone, it's gone. So there's lots of irreversibilities that we're not seeing, and we don't really recognize them, but they all lead to a tipping point. And if you don't do something about this before the tipping point, you've got a problem that you really cannot handle. So this idea of self-preservation probably doesn't become really, really obvious to everybody until you're past the tipping point. So that's one issue. Now, another way, of course, we want to look at it is, okay, we're not so selfish that we're just going to look at ourselves at this, and that's not working so well. But so maybe our theology will kick into place. And of course, this first verse gets a lot of attention. The Lord God took man and put him in the Garden of Eden to work it and take care of it. And so we get the whole idea of creation care associated with that, and that sounds good. There's a second one here that a good friend of ours, pastor, likes to point out, which is not one that's normally used, I think, in terms of this issue of creation care, from Proverbs 12. Whoever is righteous has regard for the life of his beast, for the mercy of the wicked is cruel. That word beast, depending on, this is the NIV, but depending on which translation you use, is sometimes translated as animals or livestock. So the idea here is the righteous person is going to take care of not only himself, but the livestock, animals that she has responsibility for. And that's part of our mandate, okay? So again, you see, we're told there's an environmental task that we are given here. And so maybe these sorts of ideas will kick into play and move us forward on this. But we haven't seen that yet, and I'd like to give you what I'm calling a modern parable. It's a story. I teach Gen Chem, and I taught it last term, like I've been teaching it for 30 years now, and I almost know what I'm doing. And we have various topics, of course, we cover. You probably all took Gen Chem at some point, and one of the things that you do in Gen Chem is you study acid and base theory. In fact, maybe that's the heart of chemistry. And everybody loves that, and that's why they become chemists. Or physicists, maybe, or anything else. But okay, so we teach that, and last term we were doing acid-base theory, and our students do not love it, and so and they struggle with it. No, they don't love it. It's incomprehensible to some people. And so we did a review session at the end of the term, and we did these review sessions topically. And I have a wonderful graduate student showing up here, Kaylin. And Kaylin, I asked her to lead that review session. She's really good at this. All this other stuff up here, that's just window dressing. I just want to show you the picture of Kaylin. But this is she does do CO2 chemistry. Her job is to turn CO2 into CO, and she uses these fancy metal complexes to do that. But I wanted you simply to know that Kaylin does chemistry and does a great job at chemistry. But in addition to doing chemistry, I asked her to do this because she's a wonderful teacher. So I figured she is the person that could nicely review this whole topic of acid and base chemistry and really bring it home for our students for the general exam. So I assigned her acids and bases, and a big part of acids and bases, and the most odious part of acids and bases, are buffer problems. The very same problem I was talking about before with regard to the ocean. So before I tell you what Kaylin did, I have to tell you what we do in class, during the lecture. So we've broken it down to a series of steps. Okay, this is my colleague, Rob Lesbrance, that likes to teach this lecture. And he always says to his students, Whenever you see an acid-base problem, the first thing you do is you write a balanced chemical reaction. He pleads with them with this. He says this at the beginning of every lecture he gives on this, okay? It gets to the point that they know in their sleep, the first thing you do when you see an acid-base problem like a buffer problem is you write a balanced chemical reaction, okay? You do it for all acid-base problems. You even do it for the dreaded buffer problem, okay? And again, just to make a point here, the first thing you do when you see an acid-base problem is you write down a balanced chemical reaction. Okay, so Kaylin goes into the class to do her review session. She asks the class, what's the first thing you do when you see a buffer problem? The class has got this figured out. In unison, they respond, write a balanced chemical reaction. They've nailed it, right? Kaylin answers, nope. Stunned silence. What do you mean? These professors have been standing up in front of the lecture hall for weeks now telling us this, and you say, nope? She lets them sit there for a second. The first thing you do when you see a buffer problem is cry. Got a chuckle. But I think that's sort of where we're at with respect to this whole CO2 climate change problem. I think by and large, we recognize the problem. Different people have different ideas of what solutions might be. You've heard several at this meeting. And yet, I'm not sure we have the willpower yet to do anything about it. We're sort of at the cry stage. We recognize a problem. We don't really know what to do about it. We're confused at this point. What makes sense, what doesn't make sense, what are the best ways to go? Well, assuming we can get past crying and start to solve the problem, then what might we do? And I suggest the first thing we could think about is an idea that my colleague, Rob Soklow, over there, put forward. I guess I should say our colleague. About 20 years ago now. Rob was the head of our environmental program at that time. He's now professor emeritus. And he made a plot, a very simple plot of the years here and the amount of CO2 we were generating from using fossil fuels. And he did that way back here in the early 2000s. And he had this plot, and he just did a very simple thing. He did a linear projection of how much it was going to go up as time went on. And he said the area under this curve then is all the CO2 we've generated, and that's the CO2 that we've got to get rid of. We've got to take care of it somehow. And he said, that's a big problem. That's a lot of CO2, all that green area under there. He said, but let's break it down into a series of 7 triangles. And let's assign each triangle a known technology. We don't have to develop anything. Let's just make a known technology for handling this. And the first 7 here are what he's listed. So efficiency, just start using more efficient electronic devices and whatnot. Switch to fuels that have less CO2 emissions, things like this. I guess that would include your area, right? And then each triangle, you can handle it. It makes a big problem into 7 little problems, and you can do it. And he said, we could do it right now. We have the technology right now to do this. And people criticized this, not because it was a bad idea. They thought it was a great idea, but he said, you drew the wrong curve here. That black line is way too low. And they said it's way too low because it serves what they call a business as usual model, in that we would not have an acceleration of our use of fuels for a variety of reasons and whatnot. It's just a nice linear extrapolation. And so he went back and he redrew a higher line here. Now he has to use 9 triangles to fill it out, and they're right there and whatnot. But he does it, and again, all known solutions. And again, the answer came back, we should do all of this. This is great, but still, the actual curve is going to be higher than this. And you need to come up with things that are not available solutions today if you want to use up all of that CO2. So the only thing I'll point out, given that way back, back in the early 2000s, these were all known solutions, we should have at least, if we were serious about this, implemented either the green or the orange-yellow triangles there, and we haven't. So that goes back to this question of willpower. It's not like we're missing knowledge to do this, but we really just do not have the interest at this point in doing this. And there's some inconvenience in doing some of this, and there's certainly cost in doing some of this, but we're not doing it. Okay, so if we need more than that, then we can go to my TRL level 2 things. What new things can we do? And tell you a little bit about our research. And one thing I want to point out is today, in terms of fossil fuels, in particular oil going to various things, 93% of our oil is used to make gasoline and other fuels, jet fuel, things like that, diesel. 7% is going into making materials. Materials are kind of nice in that they lock up the CO2 issue. You build a building with materials and it sits there for a long time. Fuels, of course, you burn and you make more CO2 when you burn them. But our CO2 problem is so large that if you do not make fuels and figure out how to recycle those fuels, the CO2, back into fuels, then you can't solve this problem, because 93%, again, goes into doing that. So you need a way of taking CO2 and turning it into a fuel. So another one of my graduate students has her PhD now, works with the State Department, Aubrey Harris, and she came up with an electrode, this little electrode right here, about the same size as the pellets you were talking about, actually. This is 4 millimeters across, a little bigger than your pellet, but giant. But what this is just a piece of carbon, glassy carbon, with these two metal oxides dispersed on the surface. And she used that as an electrode in an aqueous solution saturated with CO2 and started making this compound here, oxalate, in really, really high yield, 60% yield. Showed it was oxalate spectroscopically. And what was very exciting about this finding was that if you're going to make a fuel, you need to make a molecule that has a good capacity for storing energy. When you burn it, you want a lot of energy out, and that means you need to make carbon-carbon bonds. And most of the electrochemistry that's been done with CO2 does not generate carbon-carbon bonds. It generates molecules with one carbon in it. Okay, and this oxalate molecule, not a great fuel, I confess, but it makes a carbon-carbon bond. So we wanted to understand how you make a carbon-carbon bond, and this looked to us like the system that was going to do that. So we're very excited about that. Also, other people had reported oxalate, but it was a couple percent of oxalate from the CO2, and the 60% number was just mind-boggling to us. So we're very excited, and Aubrey worked on this and got lots of good results and graduated. And then somebody else took over the project, and no oxalate's coming out. Sort of an interesting situation. So by the way, we never intended to make oxalate to start with. It was sort of a gift to us. Even the surface we made by accident, I must confess. This was not the surface we intended to make, but we didn't really realize that we had the wrong surface. We put it in our electrochemical cell and it started spewing out all that oxalate. So lots of very fortunate things were happening, but then it stopped as quickly as it started. And we couldn't figure out why until Steve came and joined my group as a postdoc, and another graduate student, Stephanie, came, and they had these numbers from Aubrey. You know, there's your 60% oxalate and whatnot, and they're trying to reproduce that. And what they notice is that there are some stainless steel fixtures external to our cell, things like the alligator clips that clip the cell into our electrochemical setup and things like that. And they weren't quite as stainless as they should be. They had been corroding. And they were wondering if the components of the stainless steel might have been accidentally getting into the cell before and helping us make that oxalate. And when we really cleaned up our system because we were struggling to make oxalate, we were probably making things worse. And so they cleaned up the system, and they took these species one by one and threw them into the cell, and they put in nickel. Okay. Iron was an obvious one to try. It does some little things, but not as much. Chromium, we figured, wasn't going to do anything because chromium was one of the things on our electrode surface, but nickel. Nickel was magic. It didn't make oxalate, however. So I've been hearing a lot of computer scientists talk the last couple of days. They keep on talking about garbage in and gold out, but if they were chemists, not garbage in, garbage out, if they were chemists, and in this system, it'd be garbage in, like stainless steel components, and gold out in this case. Because when they put the nickel in, they started making a lot of what's shown by these blue spikes here, which is butanol. Butanol is not one carbon bond, it's 4 carbons bond together with appropriate number of hydrogens. And the interesting thing about butanol is a few years before this, I had gone to our engineering department and said, what's the smallest molecule that I could be successful making and that you guys will call a fuel? And they said butanol. So we're actually making a fuel now, and we can make it pretty efficiently, about 40% efficiency for doing this, which is a high number when you do this electrochemically. Just to show you what's happening here, we gotta understand, gasoline is a good fuel. And what we're looking at here is the energy density in terms of the mass of gasoline versus its volumetric energy density. And it's a good number because it does both pretty well on both these scales. You could go and you could switch over to hydrogen, which people talk about as a nice clean fuel. And that's great. It's even much better on the energy density scale, but it really doesn't make it on the volumetric scale. So you need a big container or a very high pressure to get around it. And even high pressure doesn't help you all that much. So that's 700 times above atmospheric pressure, and you still don't have a lot of energy density. But butanol is like the second best thing to gasoline. And so our cell started making butanol. It makes it reproducibly these days, and it makes it in high yields. So we're actually doing fuels. This is just an experiment, a bunch of data. It makes other things besides the butanol, other organic things. But the butanol is this blue curve right here. It's going down here, by the way, because we're running out of CO2 in our cell. We ran this experiment. That shows 7 days of run. We actually ran it. I ran out of space on the slide for 9 days. And we stopped after 9 days of running. Well, we didn't actually stop, but our equipment, our test equipment broke. Our cell was more robust than our test fixture. So we were pretty, well, we weren't happy that it broke, but we're pretty good. So it's a very robust system, for a laboratory bench type system. It makes a gas type product that we can use, and it does it very, very reproducibly with good efficiency. So there are other solutions out there. They can be implemented, and I'll just go back to my earlier statement, and that is, do we have the interest and will to do that as a society, or do we feel like we have a mandate to do that in terms of how we handle creation and our charge with regard to creation? So with that, thank you for your attention.
All right, thank you very much.
Andy, how much energy do you have to put in to get this out? And second, and where does that energy come from?
Right.
And third, how close are you to industrial scale? And we need to see the nuclear reactor.
Right. All good questions. Let me start with the middle question first. So, well, maybe I should start with that electrode I showed you, 4 millimeters. That's how close we are to industrial scale, right? So we have a big scale-up issue. Now, I feel somewhat confident that we can do that actually, in that we have in another system succeeded in building industrial scale electrodes and had a startup called Liquid Light, which has now been sold to a European company. So I know what it takes to get to industrial scale. We're nowhere near that with this system, but I can envision being there. I guess that's the answer to your last one. But it's going to take a little bit of work, a little more than we have right now. Energy. Where are we going to get it from was your second question. You don't want to get your energy from a power plant, obviously, because power plants burn fossil fuels. So you need to use solar energy to do this, or fusion energy to do this. You need right. So you need some source like that. And of course, right now, solar is fairly readily available. Fusion is not yet, but so you could use wind also, of course. But yeah, a non-traditional energy source associated with that. But that's been demonstrated with these sorts of electrode systems. So solar anyway. So that should be fine. And then what is our efficiency for this process? So I pointed out to you for making butanol, about 40% of our electrons are going to actually making this product. Now the other products are useful also, but if you just want to be focused on, I want butanol, okay, we're throwing away half of our energy, if you will, to other products. One of those products being hydrogen that can be recycled, but and then our overpotential on this system is about a factor of 2 above thermodynamics. So our energy efficiency on this is somewhere around 25%, which is okay. I could get better, but it's not 2%. So and those kinds of numbers when you do the scale up, fit in well with an industrial process that would be profitable.
Great.
Yeah.
Another question back here.
This is exciting research. Thank you. Just wondering, with the oxalates, the chromium, the nickel, and so forth, are you having toxicity concerns?
Yeah. So we're not making oxalate anymore, and toxicity in terms of the products is an interesting question. All these chemicals I'm making, I guess you could say, are toxic, but so is your gasoline. It's no worse than that. So there's that. In terms of the chromium oxide, gallium oxide, they're solids, and unless you're going to come and eat my electrodes, we don't have a toxicity issue there. And it's also a very small amount of material. It's used as a catalyst, so it's a 10 micron layer sitting on our electrode. So I would never be so bold to suggest to you that a chemical process is not toxic, but this is a quite controllable process. One of the nice things about this process is our electrolyte is always water, and that removes a lot of the toxicity issues.
Okay, another question?
How does this process that you have working compare to other work that is being done on this? Are you on the high side, or are you kind of in the middle in terms of efficiency of converting CO2?
So probably the most advanced processes that are they're in startup companies at this point, they're pre-commercial, would be processes that generate so-called C1 products. So CO2 going to a product that just has one carbon. So, methanol is a good example of that, and formic acid. Those processes are pretty developed processes. I mentioned Liquid Light and sold to this company Avantium, and they've developed a formic acid process, for example. There's another company out in California that has a high efficiency formic acid process. There's a company now, I guess it's out of Chicago now. It started up here. It started in Toronto, at the University of Toronto, but they're taking CO2 to a C2 product, to ethylene. And that is close to commercialization. That's in a startup environment. So our process is not as developed that. Those different ones I just mentioned, they have the large electrodes that you need, and they have demonstrated lifetimes that make them industrially feasible and whatnot. This is fairly new. The interesting thing about this, two interesting things: the efficiency of this process, and the fact that we're making a much larger molecule than the other processes that have been developed so far that could be used actually as a fuel.
Once you have three transition metals that are all dancing, the middle of the periodic chart is pretty wide. What's your next step in terms of something else that might do this?
Yeah. So I mentioned this nickel. This nickel, became a big question for why do you need nickel in there? And it turns out it's a three bears type of problem. You have a lot of nickel there, no good. Too little nickel, no good. You need just the right amount of nickel, and it's a fairly small amount of nickel. And so we've been looking at that a lot just to understand what the chemistry is behind that. And one of the ways we've been looking at that is we have been changing the nickel to a different metal and seeing what happens. And that's given us great insight into the problem, but it hasn't given us kind of practical information like I can make something better than butanol. So for example, one of the metals that we have put on there, very interested in, is gold instead of nickel, which sounds maybe like we're going in the wrong direction from a cost point of view, but from a chemistry point of view, it gives us a tremendous amount of information about the mechanism for making butanol. And we get different products when we do that and whatnot. And so you can play those games. It turns out these guys, these chromium, this is our sewing machine here, and we're stitching together CO2s. The main purpose for those guys is they generate a structure on the surface of the electrode that, if you will, looks like little test tubes, if you will. It confines the CO2 close to the electrode for a long enough time to carry out the chemistry that we want to carry out. And so they're there more for the structural aspect as opposed to the chemical aspect. And those materials could be changed. When you change those materials, you can sort of change the size of your test tube and things like that, but there's no catalysis involved on that side of it.
I'm just concerned, Renaud, I have a question. Have you developed any kind of consortium with companies that have a lot of CO2 and money, and I'm thinking of the energy companies that I've been involved with, that want to be part of the solution, not just a villain? Have you attempted to do that?
No, in that right now we've just been developing kind of the fundamental chemistry. I think we're pretty close to the point where we're thinking about, can we now start pushing this into a commercial sort of process? We're close to that now, and that's at the point I think that the kinds of companies that you're talking about get interested in this. So.
All right, let's thank Andy for a great talk here.